Welcome to functional and reactive operations. This will be a whirlwind tour of principles, methods, and supporting tools that can enable operations staff to succeed no matter what monolithic Rails app, legacy app, Visual Basic app, or polylith of microservices you throw at them. And it will be a whirlwind because I realize I'm between you and cocktails, so I'll do my best. So this talk is primarily about the thought process, the principles and the methods, but there will be some code in here to demonstrate some of the tools that are available today. I am Susan Potter, and today I will be your guide. So I'm a server-side backend engineer that turned to infrastructure about 6 years ago. The last 10-ish years, I've been trying to reason about code, or know when I can and can't reason about code. This kind of goes the same for distributed systems. I've tried to understand what constructions of distributed systems make sense, what kind of guarantees you can get from different constructions, and what is actually impossible, right? I'm still learning, right? But today, I kind of prefer, even though I moved to operations, which is very Ruby, Python, Bash, undisciplined perhaps sometimes. I do actually prefer using approaches that try and eliminate invalid constructions where possible. So I do like types, expressive type systems, referential transparency, parametricity, propositional logic, just to name a couple of things, which is perhaps a little bit unsettling for some people. So if that offended you by any means, this talk may not be for you. So, but prior to this discovery, this meditation and reflection, I have to repent in front of you because I contributed to this mess. I was very active as a Ruby developer and Ruby on Rails and things like that. So I contributed to the mess. So specifically what am I talking about there? I built, designed server applications without as much realistic grounding and reality, or understanding the mental models, right, of the operating environments. Involved in designs that discarded things like network latency, maybe network partitions. What are they? Do they even exist? Data consistency concerns, or actually building on top of potentially flawed concurrency models, right? So all of these things create operational headaches, big time. And so I have actually paid my dues as an operations engineer, I think, right? But I don't stand before you here as like a prefect, a jury, or a judge. I'm here as a felon, right, and to redeem myself. And so this is part of my message. And so forgive me, Reactive Summit, for I have previously sinned. So, yes, this is obligatory, right, for me. So in 1972, a prolific computer scientist who once hailed from Austin, right, gave an ACM Turing lecture called The Humble Programmer. And it is still very relevant today. I recommend reading the whole transcript. Now, put your hands up if you want to build reliable software, whether that's infrastructure or services. Yeah, I would hope so. We're at Reactive Summit, right? So, a wise and sometimes smug computer scientist once said, those who want really reliable software will discover that they must find a means of avoiding the majority of bugs to start with. So, can we avoid the majority of bugs to start with? What do you think? Okay, that was a resounding maybe, I think. Okay, so the promise of this statement is that we can make the programming process cheaper, right? This is a lesson that GM could have learned from Toyota in the 1980s with the NUMMI experiment if they listened. We might come back to that if we've got time, although I know I'm between you and cocktails. So some of the problems that we have in infrastructure is that reproducibility is just not there. Most mainstream tools just cannot create the right reproducibility of systems and infrastructure. Shared mutable state that is very commonly relied upon in mainstream tools have unknown semantics in many failure cases. So continuous integration builds. I mean, we all want to do continuous integration. Hopefully, most of us are, right? And automated builds and, deployments. But they often break when the application dependencies change, right? So if you're upgrading to a different version of Ruby or Python or PHP, these things typically break, right? And they require out-of-band configuration changes, right, to the build service. And sometimes the deployer user accounts, which is really nasty. And then, you've got apt sources or yum repositories where the package repositories themselves have out-of-band changes. So they're kind of floating references that change, right? So one day you can spawn up a new cluster. It'll have one set of dependencies, dependency tree, and then the next day, totally different. Potentially, it could kill your app. So provisioning, deployment, and in-place upgrades have unintended side effects. Who here uses Chef or Puppet or things like that? OK, quite a few of you. Now, when you run, so any questions? Sorry. OK. When you run Y-run or dry run, often there are effects that it can't actually predict, right? And it doesn't actually want to run them because it'll have side effects. So you actually don't really know, and you can't truly test before you actually do, right? And so there's some problems there, right? So instead of truly convergent, we end up with maybe one day, but maybe never convergence, right, of those systems. And then systems understanding. This is a little bit of a culture problem. So a problem that has been the root of many production system outages that I've seen over the last 6 years has been that the mental model that operations engineers have wasn't robust enough or based in reality as much as it could have been. There's a lot of FUD on the internet in terms of how Cassandra works, or this is what you do with Elasticsearch, and it's not clear to some people whether or not where they should place their trust. One company that used Cassandra to persist data for one of the highest grossing products at the company, there was numerous attempts to migrate out of their data center to AWS. Every single attempt failed. Now, fast forward a couple of reorgs and new Cassandra cluster in AWS that was well provisioned, right? And we'll talk about what kind of was used there. One of the original engineers, one of the two original engineers that was on that project, was able to root cause exactly why that kept failing, because they still didn't fully understand why it kept failing. And of course, they kept repeating their mistakes. And he could do this because he could rely on repeatedly building new clusters over and over again for the experiment that he designed. And he was able to fully root cause the problem to one control connection and one data connection, and there was a firewall in between. And the keep alive time on the firewall was, of course, less than the Linux defaults. So, of course, the control channel kept resetting, and of course, it kept having to reinitiate the whole data transfer every single time, right? So, kind of I mean, you should be able to debug these things. This should actually be pretty easy for most operations engineers, except it's not, because we can't reproducibly recreate experiments. So in software, we talk a lot about the wall between development and operations for a lot of times, and then we talk a lot about cross-functional teams. And that's all good, right? I don't actually think that's the problem. I don't think the divide between the roles of developers and operations is necessarily the problem. I think it's actually the divide between producers and management, and the motivations that are set by the top level, right? Anyway, the only reason I mention this is because it's really worth paying attention to. OK, so what yields reliability? OK, I'm going to say a really good contender is referential transparency, which is really the core of functional programming. So I'm just going to talk a little bit, show some examples of the different properties of referential transparency and how we apply it to operations. So on the top here, we've got some Scala. Hopefully all of you can read Scala. It's really just an object with two functions in it. Really nothing interesting. Functions have inputs. This is all this slide is trying to say. And below, I'm trying to introduce this syntax for Nix, which is an expression language that allows us to define packages and host configuration. So these are equivalent, right? We've got the myAdd lambda at the bottom, which should be equivalent to the way I've defined it on line 2 in the first snippet of Scala. Note that there's 2 parameter groups in Scala, which means that you pass in an argument to myAdd, and then it returns a function that accepts another argument, right? That's actually exactly how lambdas in Nix work, right? And so there's nothing terribly interesting here. I just wanted to introduce the syntax and okay, one of the properties of referential transparency is that functions have inputs. Now, we can model packages as functions, or lambdas, as they're called in Nix. And of course, these have inputs. So on the first 2 lines are just comments. Line 3 are some named arguments. And there are 4 arguments there. The first 2 are helper namespaces, and standard env is like a namespace which bundles a few different helper values and functions. And then fetch URL is a helper to be able to retrieve sources from the internet. And GCC and help to man are 2 packages, right? 2 other packages that go in to make this hello package. Now, this is just a definition. What we do here is we return a derivation, which is a description of the declarative description of how we would go about building that package, right? And the associated binaries or other files that we want to lay down. Now we can also model machines as functions, right? So here again, we've got named arguments at the top, config and packages. And these are standard things in the Nix OS environment. So what we can do here is we can enable SSH agent authentication. We can enable some security stuff like sudo. And we can start the OpenSSH systemd service, right? And this is all just declarative description of what we want to happen. And OK, so back to packages as functions. Now, functions return results, right? And so you can see here, Nix has this REPL, and like all good languages, right? So in this slide, we're just loading the Nix packages symbols into the REPL, and there's almost 6,000 symbols in there. You can think of Nix packages as a community-managed and curated list of packages and helper functions that aid in package and host configuration. So if we look at the value returned by the import, which loads the expression, and because we're using named values to it, we apply the arguments to the lambda inside of the curly braces with this inherit syntax. At this point, we've not evaluated the derivation, right? This is just the description of how we go about building the package. But you can see here, it's just returned the derivation. Now, we can actually force the evaluation. You can do it a couple of ways, right? So inside of the REPL, we can just interpolate it as a string, and it will return a path, right? So the toString is the path, is where it's actually installed on the file system. And then the second method that we can do to evaluate this is to use this nix build command, right? OK, so we get back a path, which is the path where all of the binaries or whatever files are packaged inside of that package get laid down. Now, you'll notice this ... There's a cryptographic hash there, which represents the whole transitive dependency tree of everything that went in to building that hello package, right? And that way, we don't have shared paths. We don't have shared mutable state. We don't have to overwrite anything. If anything in the transitive dependency tree changes, then the cryptographic hash changes, right? And it's written to a new path. So, OK. And the way that things like paths are, in fact, managed is all done through the Nix set of tooling, right? So it does a whole bunch of symlinks into profiles and things like that, so that you don't have to worry about having really disgustingly long paths and things like that. So now back to the machines as functions, right? The machines return a result, which is actually the whole path that represents the whole configuration for that machine that you defined in that expression. So we can do this, we can evaluate that by running nixos rebuild switch. And what that does is it actually activates the switch subcommand, actually activates this configuration into the current running machine, right? There are multiple options. We can build VM and a few other things. And if we have a look at the system profiles, you'll see that we can actually roll back as part of this because we have different symlinks for the previous configurations that we can actually roll back to. And that includes things like, kernel configuration, or like if we've modified the kernel like extra config with, some module that we needed built or something like that, we can roll back to that, right? And it can be a totally different version of the kernel and so on and so forth. Okay, so, and of course, we only depend, as part of this referential transparency thing, we only depend on inputs, right? Of course, there's global state you can refer to in Scala. So this is like being silly here, just to get the point across that in Nix, that's not really what you do, right? It kind of is possible, but it's, it's stretching it. So let's have a look at Nix. Now, the previous hello derivation definition that we saw earlier, we can take out the help to man from the named arguments, right? And we can try building it. And then it tells us, oh, there's an undefined variable help to man, which was in the build inputs in the definition. So of course, we can't build without that, right? Okay, so we kind of would expect that, right? That's just checking that everything refers to something that exists. But how about if we took out the help to man from the build inputs? What would happen there? Well, we can do the evaluation, line 8 through 12. We're trying to evaluate the derivation. And it chugs along for a little while, and then it errors out, right? And at this point, we're trying to use help to man inside of the definition, and of course, we're just not able to. So we don't get an actual result from this. This is it doesn't succeed, right? So this is invalid. And of course, when we, this is part of the testing, saying once we add help to man back, we'll be able to recompile and it'll build. But once we build it once from that definition and we've pinned down our version of the channel, we can always rebuild that, right? Okay, so, and of course, one of the other properties of referential transparency is that we return the same result given the same inputs, right? I'm trying to be fancy here with a property, a Scala check thing, but I think that's probably wrong. I don't know if I want to use equals there, but anyway, sorry. Anyway, so with Nix, this is just a silly bash script, and I'm just wild truing to rebuild it every single time, and you can see that it actually returns the same result every single time. That's kind of boring. Okay, so questions so far. This is just trying to introduce the idea of how we could go about introducing functional programming to operations. Okay. So, so we're going to take a detour back. So this photo was taken in 1972. It's the same year that Dijkstra gave his talk, The Humble Programmer, that we looked at the excerpt from. It's a photo of the GM Fremont assembly plant. It's not too far from San Francisco, unless you live there, in which case it's Fremont. It's the East Bay, right? 10 years after this photo was taken, it was shut down by GM. I once spokesperson for the multinational organization for the United Automobile Workers. Now, this is an organization that represents the workers. Once said about the Fremont plant that it was the worst workforce in the automobile industry in the United States, right? So that's quite the endorsement. In 1982, after many strikes, terrible quality control, and rampant absenteeism, there was drinking on the job very regularly, there were drugs, there were other, how should I say, adult activities in the plant. It was no surprise that the facility was actually shut down. But just 2 years later, General Motors and Toyota created a joint venture called whoami, and they reopened the plant, and they rehired, strangely, 85% of the previous workforce. Now, it didn't take long for whoami to actually start seeing radical improvements in the workforce. And it was due to a couple of things that have been studied by many different branches, from sociology, psychology, management sciences, operations research people. What did they find? Well, this is just my cherry picking of what they found from what I've read. Okay, so autonomy. In the old plant, the GM-run plant, no one was allowed to stop the line. This was something based on Henry Ford's day, right, where you just don't stop the line. You want to keep going. You'll fix the defects later, right? Now, in those days, defects in automobiles perhaps wasn't quite as problematic as it was in the 80s when, well, firstly, regulation was starting to come about in terms of safety, right? The speed, right, that most automobiles were going at this time was significantly faster than what you could do in Ford's day, Henry Ford's day, with the early models. So there were a lot of reasons why perhaps that worked under Henry Ford, but it was really no longer working in, especially the 1980s, right, for GM. So, but in the Toyota-GM joint venture, anyone could stop the line if they saw a problem. And it was their responsibility to report back to the line manager and say, this is why I think this was a problem, and I think we can do this to avert this from happening again. Now, at this point in the Toyota branch, in the Toyota plant that they went to train in Tokyo, in Japan, the managers would come back like maybe within an hour with like a prototype of a tool that they had just described to be able to prevent this problem going forward. And then they could proceed and test out whether or not this tool, this prototype, actually would, in fact, eliminate some of those bugs, right, before they became a problem. So at whoami, cords to stop the line were actually made very accessible. There were many cords installed, right? And the music that played when the line stopped kind of resembles like that of a toddler's toy. So not an alarming thing at all, right? So anyway, so then we've got reliable baseline. So parts that didn't fit the spec of the manufacturing process were actually sent back with like reasons why it didn't work for them. That was in whoami. Now, in the old GM operation, that was definitely not the case. They would try and like not stop the line, right? They had parts, and if they had to somehow try and make it work, right? And that didn't end up very well for a lot of the quality for a lot of the cars that were produced in the old GM plant. Now, experimentation, the experimentation with the prototype tools and things like that was actually a very key part of why whoami, the same employees that were hired, that were working in whoami, performed far better than they did in the old GM plant. So whoami produced higher quality cars with less people, right, and more of them, right? So that's I think that's kind of a success metric. I mean, at least comparatively, right? The focus was on trying, methods and techniques that eliminated defects before they cost too much, right? That's going back to the Dijkstra quote. And here, workers and management really did work together because their motivations were far more aligned. Management would get pay cuts before workers were laid off, and a few other things, right? It wasn't just that, but there were a number of different incentives that actually aligned, management and workers. So how did we? We're going to go back to Nix, right? How did we solve repeatable environments? That shouldn't say dev in there. I apologize. So say you want to. Okay, so this is kind of for dev purposes, because you wouldn't do this in production. But if you wanted to load like R17 of Erlang, right, which is an old version, you might give it this package name, right? And then when you start up the Erl shell, you'll see that it's actually the right version that you wanted, right? You can do the same with R18, right, with a different set of plugins that are actually defined. And you'll run Erl, and you'll get the right version, the one that you expect, right? So this is all to root, like, you know, mapping the paths appropriately and things like that. Now, of course, you can write an expression and then launch the next shell from that expression if you want something more than just specific packages. So this is just saying, hey, we want, you know, the full Git package. We want Erlang R18. We want Hex to Nix and Rebar 3 and Postgres and Elm. So this goes well beyond, you know, like language-specific package management. This is like the whole setup and the whole system, right? And this is a very useful. This can be reused for the actual host configuration that you create for the hosts that you want to deploy to, as well as for the development environment. And so this is kind of, here all I'm trying to say is if you have to pin down the channel version, right? And you can refer to the channel version by a URL that you use to download the archive that contains all of the package definitions in. But once you do that, you've actually got a repeatable environment. And so here, we're specifying the Nix packages version by this URL. And then we launch Nix shell. It loads the expression that we saw on the previous slide, right? And now it's going to build everything that was in that expression from that channel version. And we will be able to repeat this every single time. Okay, and then there's this shell hook, which is great for development environments, where we can set up like environment variables and things like that. A lot of this can actually be put into like a host configuration too. So this is also, Nix shell is also what we used for consistent CI dependencies. So we never had to worry if we were upgrading, you know, the Erlang version or the Ruby version or Python or whatever for the app. We could just go and define it actually inside of the scripts that we needed to run for our CI process. And it would always come back with the, it would always be able to reproduce the same environment on our laptops as it would on the CI servers, as it would when we deployed it. Okay, so something mainstream tools don't really allow you to do today is that kind of level of reproducibility. I know Habitat's coming along. It's trying to take some of the guarantees that are available in Nix, and that's very cool to see. But it's not a natural extension to like do that seamlessly in those kinds of mainstream tools. Okay, so this is kind of going on about the scripts. I don't want to, be in the way of you and cocktails too much. But here I'm just specifying an actual, like what I might do in a CI verify script, right, for one of my Erlang web applications. Okay, so the keys are we need to pin down the channel versions. We update CI build dependencies with app code. So we have to put all of this inside of the same repository, or a repository that we can link to another repository if we need to. There's no out-of-band converging. So if we need to update dependency for the test to run, it's all in the Nix expression, right, that we use to bootstrap the CI script itself. So you don't have to, upload a new version of the cookbook to be able to run on, your Jenkins builders or whatever. Okay, so there are other things that we can do with Nix tooling, and I've got these as like a bonus material in the slides to have a look at. So we can diff the dependency tree. So anytime that we do a deploy or we create a new host configuration, we can actually have a look side by side at what packages have in fact changed. We can test node configurations in VMs. This is all like standard tooling in the Nix world. We can test NixOS module logic. So modules are kind of like chef cookbooks to a degree. So you can have an Elasticsearch module, and you can test that in isolation in a VM. And it's fairly simple to do. And then you can do some level of security auditing, because you can actually see what versions of OpenSSL might actually be installed for any of your dependencies inside of the whole current system, right? And just to make sure that you're not using anything that has a vulnerability. So what's next? So okay, that was mostly static stuff that we can define, but the moving parts, right? We want to be able to describe programs, right? Separate the program from its evaluation and decide at runtime which way we can evaluate that program. And so let's take a look at an example. It's a bit contrived, perhaps, but so this is some Haskell code, and we can have these different contexts. We've got interaction, we've got env config, and we've got the Elasticsearch context. And inside of, we can construct this program definition that here we're going to ask which environment we want to do this to, right? And then we set the environment, and then we get the hosts from that environment using whatever service discovery that we're using, that you want to use, right? Console, whatever. We can then restart each of the hosts, right? And this is all a high-level language, right, that we define. If you're interested in the mechanics of this is just using free, right, as in free monads. You define, this line at the top is basically a code product of these three different contexts that are, essentially, some types that describe, what you want, like different actions. And then you build these little functions that lift that data representation into like the free monad, and then you can write different interpreters for it, right? You can write interpreters, you can optimize over the effective AST that you're building with this program, and you can do a variety of other things. So what that means is that we can actually defer until runtime, until we have more information, like which interpretation we want to evaluate the program with. Okay, so what's next? So that's cool. Like that's the moving parts, the deployment parts, the icky, sticky stuff. Like you can have rolling upgrades for Elasticsearch when it's minor version updates. You can have like a cold cluster restart for like major updates, and you can just can those little programs and then send it. Create your actual dry run interpreter, right? As well as the actual evaluation that you want for production invocations. So, okay, what about requirements? Well, there's all kinds of requirements in terms of infrastructure engineering that don't get captured very well, right? So we can define requirements as propositions, right? We can translate the proposition to type, and then we can implement that type. And so, of course, this is some Idris code, right? This is just the type, right? But the idea here is that Idris is a dependently typed language, and you can do some funky things with types. We'll just say that. So here we can actually name different types in the function signature and refer to it later. You will see that we are retrieving, you were given an account, an AWS account. We're given a region. We're given this X, which is a natural number, and it so happens that it's the number of availability zones that we have for that region, because availability zones can actually differ from region to region. And then we can actually say, oh, there exists an N, which is a natural number, for all like clusters such that there's like a multiple of N and X. Right? So this cluster representation is building like the hosts, right? So we have a multiple of the number of availability zones for that service that we can deploy, right? That's all that's trying to say. And then we can ensure that this is striped with another predicate type at the bottom with stripe. And I'm not going to get into the details, but this is kind of a really powerful way of encoding this. And the cool thing about this is that due to like this thing called the Curry-Howard correspondence, with dependently typed languages like this, as long as you can show that there is an inhabitant of this type for each of the cases, then you've basically proved that this requirement is captured, right? If you do the whole specify a requirement as a proposition, and then translate the proposition as a type, and then from the type, you actually find the implementation that actually makes sense, right? Then you've actually kind of proved that you can actually satisfy that infrastructure requirement. There's a lot more work that needs to go on here in this particular thing. But that's kind of, this is an attempt at trying to eliminate bugs as soon as, like before it becomes costly, right? Just to end on one story, when I arrived at one company that had just started moving into AWS, they had a production Zookeeper cluster that was in 2 zones, right? It was production 1, right? And so obviously there would be a majority, right, of in just one availability zone. So just one availability zone could have taken out the Zookeeper cluster and made it completely ineffective for anyone to use. That's probably not the infrastructure requirement they were going for, but you know, things happen when you're moving at the speed of light. Okay, so questions? Yes?
I have no idea of Erlang or most of the stuff you spoke about, NixOS, but did this sound conceptually similar to what Docker does in terms of being able to package the software?
In some respects, except yes. So yes and no. There are differences in terms of the philosophy and the approach. Docker is, there can still be some problems. You still have to think a lot about the layer caching and things like that. You can get into a lot of problems there. The defaults aren't necessarily sane right there. I know a lot of people that have wasted a lot of time there. It's still depending on, you can think of it 2 ways. It's still depending on, you know, apt or yum for the most part. I mean, you can use it with Nix actually, and you would have that problem eliminated, but you still have this out-of-band, you know, reference pointer that can actually change at any time, depending on when you build your actual Docker container, right? Obviously, you can host like a cache, like of your Docker containers, and just make sure that you always have those pre-built before you actually deploy. But then you have to think about the layers and things like that, right? So that you can actually put in production configuration when you need it, and so on and so forth. It's definitely a good attempt at trying to work, but still trying to work with the mainstream tooling. I think the problem that Docker tends to have is that it does tend to be based on top of this somewhat flawed tooling, like the package managers and stuff like that. Great question. Other questions? Yes? Yes, so you can actually build Docker containers with Nix, but you can, you know, like a Redis Docker container is about, I think mine is 24 megs or something like that, but you can also just build VMs, and it supports a variety of different virtualization engines. You can also, like to EC2, there's EC2 images and things like that that you can deploy with. Does that answer your question, or? Okay, sorry. Maybe I misunderstood.
So the minimum size of width that you can manage natively or that is intended for a VM, it's a machine, right? Mm-hmm. It's a machine, right?
Oh, I see. Like minimum requirements. I don't know. I have used NixOS on like a 4 gig tablet, but no. Or do you just mean like the size, the disk size? Yes. So it's an OS. You can create VMs from it too, right? So yeah. It is based on Linux as a distribution. Yeah. Sorry. Go ahead.
So is there any answer there for things that would typically be used, like Ansible to do rolling restarts, like things that you actually want to have a side effect happen
Sure.
just in some kind of controllable way, as opposed to sort of immutably setting up a system, right?
Well, okay, so you can rebuild different configurations, like on the fly, in place, right? And then it does the symlink switch, right? And because symlinks are atomic, right, you can actually do that configuration change. So it's not, I mean, it's immutable in the sense that you've got a content addressable package store that isn't going to get overwritten, right? Unless you do a repair or something weird happens, right, to your disk. But for example, like that. But like one of the reasons that we actually went with NixOS is because we wanted to be able to push updates to stateful services like MySQL or Postgres and things like that. Doing that with containers and things like that is a bit of or was at least a bit of a nightmare when we looked into it. Whereas being able to push an in-place update with configuration and have it an atomic switch was like a very big thing. So yes, you can, for example, you can have like Ansible like run certain commands on it if you give it the configuration to put on there, right, to use, and then it will switch the configuration, like, if that makes sense.
So is go restart these servers in order with 2 minutes in between each restart, is that actually modelable as a configuration, I guess is what I'm saying?
Oh, okay, so yes. So there are some developments underneath the Nix umbrella, the Nix family of projects. One's called DisNix, and I think there's another one, and I've forgotten the name of it. But that's to try and declaratively represent the whole infrastructure for a service, for example, and that will try and derive some kind of meaningful way of doing things. It wasn't in a state that we could use it at that point, but it's totally possible. And in fact, that's kind of what we're trying to do with Haskell, with the Freeman-Add like representation. But we're separating the program, the canned programs of doing the restarts and the cluster restarts from the actual interpretations. Does that actually answer your question?
Yes.
Yeah, okay, cool. Anything else? Yes.
I'm kind of thinking how to phrase this. I mean, I get the difference between a functional model and a declarative model. There are, and they appear to some instances. How is this substantively different, though, than, say, pushing a Puppet manifest to say declaratively, this is what I want. If I want something else, I will make another declaration. Is there a substantive difference between the two? Because it looks like you've got checkpoints that are sort of declarative states that you can roll back to. Am I reading that correctly?
Yes, absolutely. You can roll back to any of the previous system configurations as an example. You can also roll back to user profile configurations if you have different, because you can have multi-user package like management. Sorry.
But they're declarative, right? They're not saying these are a set of functions to run. They're saying this is what you should look like at this time.
Yes, yes, yeah. To answer your question about Puppet, I mean, as an example, Puppet manifests, it is leveraging or using potentially flawed like package managers, right? So you've got that to contend with, right? So it's great in a way that it allows you to use what you've already got in place on these systems, but it also doesn't get you further from getting away from the problematic semantics of those failure conditions when package corruption can happen. And we've seen not just package corruption on the file system, but package inconsistencies in, for example, the Yum repositories or the app sources. when things get promoted or updated or deprecated, and you are no longer able to cleanly provision a new server from the original manifests, which is something that I've definitely seen a lot of times, not just Puppet, but Chef and things like that. Sure. I think it's cocktail time, unless there's a pressing question. Yeah, no, this is all about me. It's all about me. Thank you. Yeah.